So today we're going to be talking about multi-agent RL and reinforcement learning from human feedback. It's because we've kind of, not on purpose, but like been slightly avoiding partly this topic for a little while because it's kind of complicated. Even though we've talked about doing RL, we've done a lot of like collecting data from people, training a lot of different models. But let's dig a little bit more into like what is some more of the fundamental background for understanding multi-agent RL. Because to be honest, like the general robotics problem is a big, ugly multi-agent RL problem. Figuring out how to do this is at least tricky. And we'll talk about some of the like more general strategies to be able to approach making like the overall multi-agent RL problem a little less complicated. So there's some more obvious places to assume structure, some ways to kind of adjust the optimization or to make it easier. And then this actually leads kind of nicely into RL from human feedback. And instead, if you have got data sets from people and you're trying to figure out their intentions, then how do you learn a model to be able to replicate, their preferences, their intentions? Okay, yeah, some overview for today. Um, we always kind of look at this particular, diagram again, because this is the very simple form of doing RL, just collect a lot of trajectories, be able to optimize some policy. But a bunch of these things are unknown, but they're basically even worse. There's a worse version of this thing that's unknown, where here, everything we've talked about is sort of whenever an action is taken, don't worry about it. Then basically in this case, there can be a lot of things that happen in the world that are not under the control of the specific agent that just took actions. So in this case, because of that, this is like the multi-agent problem where, it's like the challenge of being able to get to school here today. If you drove, there's a bunch of other agents trying to figure out their own paths to their own spaces they want to get to, and then how to like plan and negotiate how to get to where you want to go in spite or maybe, not against, but with all of the other agents that are interacting in the world. Okay, so what are some examples of multi-agent environments? You can't use car driving, I just gave that one. So what are some other examples? Going right for politics today, are you? Sorry? Yeah. hmm That's a good one. And there's a lot of people that are studying versions of this right now. Because there's a lot of possible benefits. Like there's a couple of my colleagues in reinforcement learning, they're looking at, okay, if you make a certain type of like political simulation, like can you figure out how to maybe like change tax incentives so that people will end up like pursuing more, carbon neutral or carbon negative, sources of energy in the future, or maybe how to figure out stuff related to other types of political challenges. But from those, you need to figure out like how do you simulate an entire society and the decisions they make. So the simulators are, I mean, they're good and well motivated and usually grouped in with some people who are like from economics. So, and then you just need to figure out how to train an RL algorithm. Short story is very few just blank RL, basic RL algorithms we've talked about will work like out of the box on these political types of simulation problems. Okay. Other types of multi-agent RL problems? Ants? Ants. Ants. Hmm. Oh. Okay, I'll let that one slide for now. It's just complicated because ants, like there's worker ants, there's a very specific design in the entire like organization for ants that we could probably spend a long time talking about where that is a multi-agent problem and where it might not be a multi-agent problem, depending on the way they interact. Okay. Yeah, sorry. Oh, there's a Zoom person. Yeah. Search and rescue with drones. Hmm. So you mean like, yeah, with multiple, let's just say. multiple drones.
Yep.
The drones have to interact. They have to figure out how to plan, things like that. Hmm. Uh, so I guess kind of even related to the ant problem. So that can be treated as a multi-agent problem. It can also not be treated as a multi-agent problem. But there are like positives and negatives depending on how, yeah, that wants to be modeled. Okay. How about one more? I know you don't all think about multi-agent problems to keep you up at night because they're really hard to optimize. Uh, research projects, class projects, maybe. Good example, people. Um, class. Sorry. Uh-oh. Okay. Sorry. I'm looking at you, so I'm not exactly seeing the suggestions from Zoom. Intercepting enemy aircraft with multiple jets that coordinate. Uh, that's a suggestion. We're going to not use that one as an example for today, though. I have enough problems with sleeping at night. All right. Uh, there are, yeah, definitely some of these. So these all have, I just want to get even kind of related to some of the discussion that, like in the discussions we were having on Wednesday of like figuring out classes of problems. So we talked a little bit about, at least some of you went after the question in the discussion of like, well, whether or not to use like a foundational model or sim to real, and then what task it might be better for sim to real or not. So understanding like, okay, how multi-agent is your problem? Well, then if you know it's very multi-agent, you're going to have to use some of the algorithms we'll talk about today. And normal RL algorithms are not going to work for various reasons. Okay, so these are good examples. Yeah, definitely soccer, self-driving. And this is another example too. Maybe some of you have heard of this. This is the robot soccer competition, which is way better than the human soccer competition because this is much harder to do. Um, but there's a couple of different leagues, so people are very interested in this. This is a fantastic area, and there's a bunch of simulators to like try out algorithms, and if they work well enough, even use them on, I think it's like 5-on-5 humanoid robot soccer. Uh, this image doesn't quite convey though how slow it is, but it's also still pretty fun. Okay, so what happens in this case for, all right, we've been talking in the class so far where there's always an MDP. There's a Markov dynamic process. It's got a nice formalism. We can use reinforcement learning in order to be able to optimize for a Markov dynamic process. But in this case, this changes when there isn't complete information. So even if you're playing something like soccer, you don't know what the other team's plan is going to be. You don't even know exactly what the intentions are in, the other opponent's minds. Hopefully you've trained with them well enough to at least have some idea about what your teammates are thinking and what they're planning. But because of this, basically there's always going to be this form of partial information. And as soon as partial information comes into the mix, then there's going to be a partially observed Markov game. And now instead of having what we referred to as states pretty generally in the class, there's just observations. You only get to see, or the agent only gets to see a small bit of information about the world that it is learning how to interact in. And then this just changes a bit of the notation that we'll be using for today. So here, like the I up at the top is going to be the index for the agent. We'll still keep like the subscript on the bottom for time. And then now the idea is to figure out what's the next state of the entire universe, given the last state, which could somehow be inferred from a bunch of observations, and all the actions from all the other agents. And then here, the general form of this is every agent will also get its own reward at every single time step. And the overall problem is just changed a little bit. We're now argmax sum. This has got an I on it. So like maximize the parameters such that that agent I ends up getting the best reward with respect to its actual reward function. And then in general, you can just like sum this over all possible agents. And then this is the optimization objective for, kind of general high level how this is adjusted. Does that make sense so far? Any questions? Yeah. They don't have to have their own policy. And we're going to talk about some weird versions of this today. Well, there'll be like shared chunks of policies, and that can help a lot in the optimization process. Okay. Is that a question or just a thoughtful pose? Okay, great. Sure. We'll get more into the details now and then see how this basically unfolds. So the real question is, besides the fact that, the agent is going to deal with observations now, what really makes this process more complicated? So a lot of it is now figuring out how to estimate even more than what was trying to be estimated from before. So this, I want to basically here, let's unpack this problem. So before, when we're just doing MDPs, there was just the dynamics, and we mostly talked about them as if they're just like the physics in the environment. The agent's trying to figure out if it takes an action, does the water spill out of the cup? Does it move a little bit? Something like that. The real challenge is this dynamics now like can include a lot of stuff that will at least have to be perfectly estimated in order to be able to find an optimal policy. So you can kind of think of this, short form of this, all these actions that are going to determine the next state, each of them come from some distribution, some policy from a bunch of other agents. So here, this means that not only does the agent have to figure out its own dynamics for just performing its own task, but those have to be with respect to what other people are doing or other agents inside of the environment. So sounds like a pretty hard problem, doesn't it? Like it's almost like first figure out how the entire universe works before it can even start planning. And the other universe includes a whole bunch of other agents. And in the general case, all those other agents are learning at the same time. So those distributions for all those policies are not stationary either. So this is, in general, a pretty challenging problem to be able to solve. And this is kind of the crux on this is, yeah, all the other agents will have like this just generalized challenge. And here, this is even kind of a specific version where it says like all the agents are sharing the same action space. In the real world, that's not always true. Like some robots can even perform different things inside of the environment or use different action spaces. So we won't cover that part today. That part's going to be next Friday about what to do with like if you do have a collection of like it's like for the example for giving multiple drones, but you could have drones and people and like wheeled robots also working together to do some kind of search. And then maybe because it's working with people, so I'd have to figure out how to interact over the policy distributions for how the people are a part of that search pattern as well. Okay, this, at least mathematically, is this optimization problem. There's going to be some distribution, some stationary distribution for the states the agent will visit for every single agent, integrate over all the actions for all the agents, and then figure out how to compute a gradient for this. So sometimes it's nice. Like in mathematics, we can write things down, even if many of the things here are very tricky to be able to estimate. But let's start here, and then we're going to put a bit more structure into this in a couple of different places. So this is where each agent itself also needs to figure out how to estimate its own environment. It needs to estimate the other agents, and those agents are also going to change the way they behave with respect to how the actual individual agent would be learning as well. So there's a very kind of entangled cyclic system of how the agents will learn, and the changes of these will change between updates. So like to connect this back to the hierarchical reinforcement learning that we were talking about, where you can kind of picture that as two agents. One is doing like the low level control and it's training to figure out maybe how to just grasp objects. And there's another policy figuring out what goals to give to that agent is a version of this problem where now the policy that's below figuring out how to achieve goals is going to be changing its dynamics as it experiences new goals, gets new trajectories, gets some more updates. And then the policy on the top is going to now figure out, well, unfortunately, what it gave some goal from before for what it was doing. Now giving that same goal goes to a different spot in the state space, leads to different rewards. So the dynamics can be constantly changing. Like I said, it's very difficult to do in optimize in practice, but This is the goal because this is basically how the world works. I think we're slowly getting to this in terms of maybe we'll get around to this when using foundational models. At the moment, most foundational models are already like extremely large, pretty hard to be able to train. So they're going to be a bit slow in order to be able to accomplish this particular problem in general. That'll be a bit more of like future research to be able to optimize even for a foundational model. But as we'll talk about in the second half of the lecture, like even fine tuning a foundational model using some forms of reinforcement learning is difficult at best. Okay. All right. So let's get back to, don't worry, there is definitely some hope here. And there's a couple of different algorithms that make this easier and a couple of different ways to think about the structure for these algorithms. All right. So let's talk about the first one. So one of these bits of structure to start with that often helps. So now a version of this is where the agents, there's usually a distinction between different types of MARL environments. There's cooperative ones, there's not cooperative ones, and then there's a couple of teaching examples as well. Where this would be, if you're playing on a team, you're all on one side of this team, you're all sharing a reward to be able to score a goal. So you probably have already a better intuition about what those other agents are going to do inside of that system. So if there's some shared objective, even if it's at some level, so like maybe, I don't know, we all want a prosperous society, so hopefully we all share that. Um, but then there's going to be more, specialized things. Well, some of us think robotics is going to be a solution to that. Others will think, you definitely have to have more versions of art so that there actually is some type of society. So there'll be some specialization, but at least if there is part of the reward system that is shared and overlaps, that does provide some uh, common information that can be used. It's partly because when you can transfer the intentions to other agents, other people, it's most likely they're trying to optimize some of the same objectives. So there's going to be a smaller distribution over possible policies that will come from the other agents because they're sharing some portion of rewards. Okay. Does that make sense? Hopefully. That's just the overcoming of the fact that, it's just kind of like how you tend to get along more with people you grew up with or people even from the same culture because you've got even like more things that are aligned and you know a little bit more about what you expect that they might be interested in. It's basically that same process. Okay. Other ones are types of constraints. So here, even in this example, if these are kind of almost like examples of the rewards, but they can be more hard constraints in the environment. So here, there are some that can exist. Let's just say this is sort of like the velocity space for some wheeled robot. You know, there's going to be some limits on how fast the robot can actually travel. So then you can add that as a known constraint inside of the environment, such that the robot, like there won't be versions of the policy distribution that go outside of that. Also, a lot of agents can't fly, things like that. So this implies a couple of different types of behavioral constraints and things that where like the probability distribution for states can even start out from. Okay. The one that's sort of a similar example of this is maybe there's some other dynamics that can be assumed about the way the agents are actually going to interact. So if we're talking about that soccer example of being able to train robots to play soccer, okay, the morphology for them can be assumed. So then there's an understanding of everyone's general physical limits and dynamics inside of the actual simulator. So then you don't need to model like any possible type of behavior that could come out of the agent in any way, but at least be kind of like constrained by its physical construction. Um, and that'll determine now like a smaller distribution of possible forms that the forward dynamics function can actually take. So this is all like shrinking what could be the giant state space that could exist and all the different types of forward dynamics hypotheses for forward dynamics models that could exist. So kind of like anything that can be done to shrink this, but not actually take away from like the general problem that's trying to be solved. So like even in that soccer example for playing RoboCup with a bunch of robots, like in that case, if it can be assumed that all the robots are the same, then you know a lot of the dynamics on all the other robots. So you can reuse a lot of the same policy parameters potentially across quite a few of them. And that'll make a much smaller version of possible things that could be learned. Okay. And then from here, one version of this too, and now we're getting more into algorithmic versions of this. It depends on how much information sharing can be done between the agents. So for example, I don't know, I'll pick on some people. Okay, maybe if I'm playing on a team of robots and then maybe someone with some sort of brain computer interface also puts that on top of the helmet that I'll play during the game. But then it means like, so there can be like instantaneous transfer of information between myself and the other agents during that actual game, or at least my teammates, not the ones that are on the opposing team. But this is like extra information. You don't need to infer, in this case, what the intentions of the other agents will be if you can have like a copy of the parameters that currently describe the other agent's behavior. And if you can do that, this helps a lot. It's very rare to have total access to like another policy, like another agent's complete parameters, even if that would be that's the much further end of like good things to have, but can be fairly limiting. Okay. And this is a very rich area of doing multi-agent RL. So if you want to get into even more of the details besides these ones that I'm going to cover in more detail now, then you can go and read some of the recent work in a couple of survey papers. Okay, so let me get into one of these. So one of these is we're going to talk about is self-play. So here, I don't know how many people, maybe for example, think to yourselves and try to work out different types of maybe math or reasoning things. But this particular version has been used quite a bit in order to solve some multi-agent problems. So the idea is, okay, consider there are two agents. They're competing in the same objective. So they're kind of like two-player games. Some examples of these are like playing Go. Wrestling is mostly two-player as far as I know, chess, etc. But the idea is, the objective of both of the agents on both sides of this actual game is basically the same: win the game. And one way to do this, in here calling it self-play, is like basically play the game against yourself. So if you could clone yourself, put them on the other side of the board, start playing the game against yourself. And then the version that ends up winning more often against the other versions of yourself ends up being the better one that we want to like reinforce and make the parameters like more similar to the distribution for the agent that keeps on winning games against itself. So you can slowly climb up this ladder of like improving against yourself over and over and over as you can play against, yourself in this case. So here, this has been used in actually many pieces of work. One of the earlier ones that was also very interesting and a bit different than at least Go and chess is this wrestling example. So here, like a lot of the environment structure is already known. So the agents have the same objective. Here for wrestling, it's basically like push the other agent outside of this wrestling arena area. And then if that happens, the agent that was not pushed out gets a point. And technically, only one policy needs to be trained. So even though it's a multi-agent problem, the goal is really to get like the strongest agent out of this. So there's only really one policy that exists. And then from this, though, what needs to be understood is how to generate this distribution of opponents, like variations on yourself. So maybe you can think of it as you'll play against yourself and then maybe yourself from each day for the previous week amongst the things that they've learned, because they're all a little bit different day to day. And then see, like on average, if you faced against all of those versions of yourself from the past couple of days to a week, like which one of these 8 or so people ends up getting the most wins against all the other versions. And that one winner is good, and then we'll basically try and increase the rewards and performance for that one winner. So this training process of basically starting to play against the agent against itself and then also against some small variations on itself is what becomes this distribution over possible agents, and it makes it a version of multi-agent RL. It's not a complete version since there's a lot of structure that can be taken advantage of here, but it is definitely one of the ones that works well. So this was also used for Alpha Star. This was also used in the Sim to Real paper that we were covering in the discussion on Wednesday. This idea of just like there's two agents, but they're basically the same goal. Can use this somewhat simplified version of multi-agent RL in order to be able to train a policy to perform well. Okay. So this algorithm it's really only got a couple of steps. There's one of this question of like, okay, how should opponents be sampled? You know, if the idea is to play and build on the agent's actual experience, it probably shouldn't sample agents that are from like really young in its life. So like in my example, if I'm learning to play chess against myself, I probably shouldn't sample, like 1 year old me for playing chess. I'm not going to learn a lot from that example. So you want a distribution still sampled from like what are skillful players so far. So at least in this paper here that we're discussing, what they did was a little bit of a variation where if there's a current policy that has been trained so far, add a little bit of Gaussian noise to like the entire parameter space for that policy, and then play against those different versions of the policy. So this one is not a significantly complex way of being able to, be able to generate some of these multiple opponents, but this is one way in order to be able to start. And then from this, select some actions given. So like this is one of the policies, and then here there'll be for like the distribution over all the other policies. So it's kind of roll out n trajectories for t time steps, and then n I think would often correspond to I. So kind of like play one game against every opponent that's inside of this distribution. You could probably scale up that number if you have the compute. Doing this usually increases the amount of trajectories that need to be collected by an order of magnitude, because it means technically every agent needs to play n games against every other agent. So it becomes basically n squared in the amount of trajectories that are collected in order to get some good information about all possible versions. And then the actions in the environment, because now it's sort of like this policy that's been selected to choose the actions for the agent or the enemy. It's not really being learned. They're kind of embedded inside of the environment. It's just like what the environment does because that agent was set at the beginning of the episode, and it's not technically learning. It's just running inside of the environment. So you can really just think of it as internally to the dynamics of the world. A little bit, the agent can be a little bit ignorant of it. There's some agent that's picking actions, but it really determines the dynamics less than the individual understanding the actions. And then from this, yeah, do a policy update. On policy, collect all this data together, do an update by basically the agent will get a reward of 1 for however many games it wins over all the distribution, and the agent that wins the most games is the one that gets the most rewards. And then that's what's used to basically compute a gradient over all of these sets of network parameters. So rather large gradient. Okay. Questions? Pretty clear? Hmm. Okay. So this is sort of, so like self-play has been around for a little while, and like, partly because a lot of the assumptions that go into it. So it's not like the most intractable version of optimization for MARL. It definitely has its limitations. Like this tends to only work when it's a self-play game. Like it's a very symmetric game where there's like a winner and a loser and nothing else. And then you can use this as a way to be able to optimize for an agent. So it doesn't really work in stuff like figuring out how to drive a car across the city, because the agents don't win in those cases. The idea is to get like somewhere faster or slower, things like that. Yeah. Mm. So no to the first question. So if the other agents have a different subset of like moves, action distributions, and this isn't self-play, It kind of like literally has to be a copy of the agent. All the dynamics, action space, policy space, state space has to be the same. So that's where it, uh, so I'll say that as just like the general form of this. There may be a more specific paper that figures out how to factorize it, but it's still a variation on this algorithm. So this, as it's called self-play, wouldn't be used there. But then I think you had a second question. What was that? Hmm. Yeah, you can usually add some noise in order to overcome that. It's like, do you also mean, like I think in chess, the white player always gets to go first, or the person for the white moves. But you end up like swapping positions in this too. So you could start out as like the white opponent versus the black piece opponent and go back and forth. Just like swap those more often, so you end up getting self-play. So like if you were going to do that for this algorithm, you might just add like another loop up here at the top or something like that that says like, and then also assign the two players to either like, you know, black pieces versus white pieces and do that kind of randomly if you know that's an extra thing to optimize. So I think something like that is also true for Go, although I don't know Go as well as I know chess. Yeah. Okay. Yeah. Other questions, thoughts? All righty. Um, so this kind of gets to the next point though. So this is kind of like the version of MARL where we've got the most assumptions. So let's start relaxing some of these assumptions and see where we end up. So what if the agents are more general? So they're not exact copies of themselves. So this is because in general, we really want to have this version of like multi-agent RL that can be used in algorithms that'll work in any type of problem. So here, in most environments, in most setups, there's a bunch of independent agents rather than doing the self-play. But this starts to ask the question, you know, how can this agent even be optimized for all the different agents? We had that like giant integral that I showed a couple of slides back where like technically you could compute a policy gradient for this. If you reach way back into your memory, you know, normal policy gradients had a lot of variance, and being able to improve on them was a lot about dealing with variance. Well, now there's even more variance because the other agents in the environment are learning and changing. So the possibility of actually getting signal instead of just a whole bunch of variance across changing distributions is quite difficult. One way to do this, though, is to figure out, okay, is there another way to take this giant multi-agent problem, see if it can be converted into some version of a non-multi-agent problem. So let's say, for example, we've got an agent, and this is just for the policy. This policy takes in a state. We'll call this like theta 0. And there's some other agent that's learning in the world. This, right, this will get some observation for 0. And this is going to be different observation for agent 1. And the other set of policy parameters for agent 1, these are all producing actions. Is there a way to maybe construct some network that this ends up basically looking like just a single agent again? Does that make sense? Anyone have some ideas? Maybe I'll give a bit of a hint. So this, uh, some other giant network here, and let's say this is a Q function. Is there a way to construct a Q function from this such that all the agents can actually learn? So if we've got policies, and let's say, at least in this example, there's two agents in the environment. It can be self-play or whatever. Those two agents have their own observations, but those observations are enough in order to be able to cover like what's good enough to be understood in the world. The next part is it also needs to understand what actions those agents are taking. And then can a Q function be constructed from this? So here we can have this step where, okay, like normally a Q function is just, you know, Q of S comma A and takes in some state, an action, and then outputs, you know, Q value. So actually, we can do basically this same process even over a large collection of agents to some amount, because to figure out, we need to be able to figure out what this Q value would be if part of the action changed. So in this case, what could happen is kind of carry these actions forward into this giant Q function. Also need to include all the observations. And now this Q function has access, at least information about how the state changes, what every agent in the environment sees, and how its current action distribution is going to behave with respect to the policies so far. And then this will basically be some sort of large Q function. For right, this is going to be a bit tricky. So this becomes a state. The state can basically become equivalent to like O of 0, dot, 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 O of n. So if you kind of group the observations together of all the agents that exist in the environment, it's pretty close to being able to determine the state. So let's just say that is enough information to determine the state. And then from this, you need the actions from action 0, comma, dot, 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 all the way to the actions of n. And now this is an actual Q function. Like we've used this thing. If you look maybe from far enough away from everyone in the class, like this just looks like what was done for homework 3. Like just learning a Q function, it's what's done for Atari. It'd be, and then here, for the most part, the algorithm, the network structure doesn't notice much of a difference. It's a bit weird, but it's one way to be able to construct a Q function from this. Does that make sense? This is sort of, I guess you can look at this last problem. It doesn't make as much sense for the self-play example because the agent is exactly the same. But if there are multiple agents in the environment and it's possible to be able to access all their policies, then we can take the outputs of all their policies, feed them into a Q function, and then use those outputs to determine how like the environment is going to change. Because the agent basically needs to be able to ask these questions in order to compute gradients. Okay, if like agent 0 here changes its action in one direction, does this Q function go up or down? And if it goes up, good. Then you propagate the gradient for that particular action value back to the policy. So you can compute basically Q of S, comma, we'll do like this gradient for A0. And then this can get propagated back through here, back into this policy, because it'll eventually train this Q function that's good. And it knows whether or not you change any of the action inputs, you can compute a gradient for that at least chunk of the inputs to the Q function. Okay, yeah. It is in the examples that I'm going to use today, but there's probably no reason why it strictly has to be that way. As long as, because here, like the deep learning just sees this as like Q learning or like DQN, or in this case, this kind of looks more like TD3 that we've talked about. So you can use different amounts of actions, like different action vector sizes. The part where this may not be great is, well, now the Q function is very specific to the number of agents in the environment. So here, if you want to add one more like player to a team, you might have to retrain this Q function from scratch because it's got a fixed dimensionality in its input. Is one of the parts that makes this a little less generalizable. So if you don't know how many agents you'll use in the future, this one's hard to use. Okay, other questions? Okay, so let's look at this. This is the diagram part for the motivation. So this basically is formulated in a couple of steps. So you can look at this paper, which is a really nice paper. Like basically this algorithm, multi-agent deep deterministic policy gradient, has been used a lot. It's pretty, I don't know what we call it, like solid. It's pretty well formed. It tends to cover a lot of the problems for multi-agent learning, sort of except for that last one for dealing with the number of agents. It's called MAD-DDPG. And then here, there's basically this policy gradient for an individual agent. I thought I fixed this. This was supposed to be an I here. And then basically being able to compute the gradient for that individual set of parameters for that agent is dependent on this function. given all the different actions from each agent. A deterministic policy gradient is very similar. Okay, I fixed that notation. And then here you just say, look, this is basically that last step. So I was describing like this little, you know, backwards line that's computing the gradient is now this equation. So here, figure out for if the action is coming from this specific policy, this is how this is determined. But then to figure out how to change the actual parameters for theta for that action, just do this backwards and then compute the gradient from the Q function, assuming actions came from that policy, and then be able to update that overall policy with respect to the Q value. And then the last tricky step that's always related to this, still need to be able to train the Q function, which is a bit more odd in this case, but not too difficult, because we still need to compute targets for the Q function. So it's basically you want to minimize like Bellman error here with respect to some target value, and you can do it for like a specific agent. So let's just talk about like A1 here for doing the Bellman error for that one agent, an individual action. And the target value is computed like reward for that particular agent, and then the Q value for that particular agent at the next state, and then all of these actions for the other possible policies. So the bottom line is actually far programmatically kind of annoying to do, because remember, you need to get actions from all the other agents. So actually this requires like querying the target networks for all the policies for all the other agents, querying the target networks for potentially all the other agents for the other environments, and then using just the actual target network for one agent. But in the end, it's just one update for this specific agent in order to be able to minimize the Bellman error. Okay, does that make sense? It's kind of like, you can sort of think of it as like, okay, there's many agents, you basically need to vectorize all the previous operations that were for one agent. It's pretty close to what is done here. Okay. Any other thoughts, concerns, questions? Okay. So this also has one extra nice benefit. So I'll say like some of the people that first saw this paper, they were, I'll say maybe somewhat combative, because like MARL, the multi-agent RL problem is always, okay, figure out how to train agents in a general form so they can run in the actual like environment, not have to rely on each other. And this actually struck a really interesting balance between, okay, so there is this centralized training process. There's this queue function that needs information from all the agents in the environment, and it needs all that in order to be able to actually train the agent. And most people would say, okay, this just looks like way too much information. You're never going to have access to the outputs of every single policy in the real world. So then how are you actually going to use this? But it has a little subtlety where there's decentralized execution. So by that, basically what this process means is, sure, the training process has more information that might be normally easy to acquire in the real world. But once it's trained, all the policies act independently. So there's nothing that necessarily there's no information shared between them at that point. So now you can deploy it in an entirely decentralized fashion, even if it was trained with a lot of extra information about knowing all the other agents' queue functions, basically, and how they'll work. So this is why this is one of these nice trade-offs here, where a queue function will be learned, where this is normally like the same network for outputting these Q values. And there'll be a set of observations and actions for each agent. But in the end, during execution, it's just this red part. Like it just needs all the policies, they'll all act independently. They can even exist on different robots. They don't really need to have much information that's shared. So this is certainly one of the nice paradigms as a balance between this, even if training requires a lot more information than normal. And this is also good because these kind of decentralized systems, here it says like less prone to disruption. They're usually a bit more robust. So if centralized information sharing is needed, then it's really hard to like keep those systems working well and not encountering issues. For example, if you're trying to do like the multi-robot search and rescue, and then there's a lot of communication delays between the robots and it's trying to train, that's going to cause even more variance into trying to figure out how to train the agent. Usually at least like reducing greatly the optimal policy that could be reached. So you'll get a better optimal policy if you have better shared communication without any latency. In the worst case, I won't train at all because there's way too much kind of disrupting the ability for the agents to communicate with each other. And here they're just communicating like actions, things like that. Okay. Thoughts? Questions? Make sense? Okay. It's also not too challenging. Well, okay. It's not too ugly to implement. You can usually like go and grab some DDPG code and then just start making like the outputs of the networks like an extra vector, and you can start training things and it'll work pretty well. The parameters for all these policies can now be different. They can all have their own reward function as well, and then you can optimize this uh, usually a lot more stably. More gradient updates usually with with respect to the order of n now that you have to train n policies. Okay, how are we doing? All right. Uh, hmm. I guess I missed putting that slash there, so that's not correct. But there's a newer version algorithm on this called Lola, which doesn't use DQN. And I'll fix this citation later for people that want to go look into it. But it does rely on a bit of information about like still having like the other agent's model parameters so that you can like fake computing a gradient for it. But it's a slightly very different version of a multi-agent RL algorithm that's also pretty stable and has been used quite a bit in terms of optimizing agents. So it doesn't use a Q value, but what it kind of does is figure out how to adjust gradients for the other agents such that they all align a little bit better. So basically, in this case, this agent has access to the other agent's gradient, not necessarily the parameters for that policy, but if it knows the gradient, it knows a little bit about how it's going to change. And then because of that, it can optimize better and find a better solution. Okay. All right. Now let's take a break for a bit. It's already 1:57, so we can start back up at 2:07. Okay. Um, there, is there a water fountain? Yeah. Oh, thanks. You're just going to use the one in the cafe? Okay. Hmm. So a limited data rate. So it'd still be a fixed data rate. Hmm. You can. I don't think that's been specifically done for MAD DDPG, but there's a couple of other papers here. You can look up this work and some other stuff by Forrester, Jacob, that has done some work in here about like one is like literally learning communication paradigms like between agents, like start them out in the learn. I don't think though he's done specific stuff on like limited bandwidth communication, but I would suspect there's a couple of papers on that, of like figuring how to communicate if the amount of bits you can transfer is only so much. In fact, I think Giovanni might do some of that work. Giovanni Beltram at Polytechnic here, because he does a lot of space robotics with limited communication and computational abilities. Mhm. Yeah, so there's This is a really open area. Like there's so much work that can be done and improved for multi-agent RL algorithms. It needs a lot of data. If you remember in the beginning of the class, we were talking about like sample complexity. So a POM-DP is another level of sample complexity upon, beyond it, where it's in P space in order to be able to do well. So that's why often there's like a lot of assumptions made in order to be able to optimize some algorithms. So like here, it's like access to all the agent's policies, and in Lola, it's access to the agent's gradient as a way to understand how it's changing its plan a bit or its policy. So there's not a lot of generally well shared multi-agent RL algorithms that work well. Most of them have some trade-off between like knowing so much information about what's going on or the other agents. Although I do think a lot of these are biologically motivated a bit. I mean, if we didn't share any similar objective at all, we'd probably have a really hard time communicating and a bunch of other stuff. So I think a lot of what makes like society and like groups organize well together is like, okay, no, we all want this thing to happen. And then because of that, it's really easier to understand the actions of other people. 'Cause otherwise, it'd be way too complex. And that's maybe going back to your like question about ants for, because the queen directs a lot of the stuff for ants, and then there's like a lot of pheromones used. Yeah. So I'm still trying to figure out how to do that for all of my students, but I'll let you know if I can make everything that predictive controlled. Yeah. But have a look. You can let me know what you find. I just don't know of any work specifically on like for like communication under hardware constraints. Yeah. I mean, I would start with people that are doing space robotics because they like work under some of the most constrained environments, and it is a multi-agent problem. And it's also space is a great place. Well, okay, it's a space where robotics are great because it's much easier to send a robot than a person. Hmm. Yeah, you need mesh networks, which is like a version of this. Um, it's where you basically make a giant self-connected Wi-Fi network across agents, and as long as there's some connection to you, then you can communicate with it with all the other agents in the network. Hmm. Okay. All right, everybody, let's get started again. A little break. All right. So one subset of multi-agent RL is a really popular one in the area of basically human and robot interaction. So here, there's a bunch of use cases for this. I mean, one, maybe you want to do arm wrestling competitions with a robot for some reason. I don't really know where I got that image from. But often, like robots are, in the end, the idea is that they probably help us with the stuff that we want to do. You know, like whether or not it's carrying your groceries or like helping build a house, something like that. The idea is the agent still needs to like understand the intention, like what is it that the person is trying to communicate to the robot in order for it to like understand what to do and then be able to do that well. So in these cases, sorry, usually there's more that's already known about the environment. So in this case, there's like one agent in the environment, one person very often. And what the agent is often trying to do is there's like some set of parameters that basically determine like the human state or preferences at that particular moment. The robot's trying to infer from some short data what those preferences are so that it can actually do an aid with those actual like tasks that are being performed. One way you could probably think about this is we've talked about goal conditioned RL for like half of this class. All of those problems are always like we had to hand type in the actual goal for what the agent would do or provide some image. But now what if the agent could just like watch maybe a bit of how you're behaving and then figuring out how to work with that actual person. And it kind of like infers what that goal is and how it should collaborate. Um, darn, I really wish there's always a nice video from like behavioral sciences where there's a kid that's about like 1.5 years old, and then another person like trying to put their books away like into a shelf. And even that 1-year-old kid can start to infer like the goal for that adult-sized person that's just trying to put things away. And the kid will walk across the room and like open up the actual bookshelf for the person so they can put it away. So this is kind of like the concept here is like just from data, just from observing the other agent, what are their intentions? How can it assist us without actually, having to be so explicit about what needs to be done? Probably the goal of like, I don't know, any good collaboration should get, to this point and beyond at some manageable time. So this is a lot of figuring out how to find like this, somewhat figuring out this set of parameters. This can still be extended a lot where the policy could learn a lot about the actual agent. The robot could learn a lot about the human's intentions, not just like some vector that describes goals, but we'll talk a lot about that example here. Okay, so there's at least one of these examples that I find pretty interesting. So I'm going to show you an example called X to text, where this was, okay, figuring out how to infer intentions using a typing interface using user feedback and actually brain signal controlled user feedback. So I'll give an outline for what this is to get into one of the details. So this was like years before Neuralink was actually a thing. This was a project I was working on during my postdoc. But the idea is like, okay, there's kind of like two problems in this particular work. One is the signal that's going to be inferred to understand the intention is pretty noisy. And there's also very little data. So this is kind of an even harder version of figuring out like how to do this human robot interaction. So here, this was work with a couple of colleagues, and I'm just sort of like waiting for some of the slides to finish loading, where you can think of in general this problem. In a second, a picture is going to load here, and it's going to be a picture of someone's eyes trying to look at a particular spot on a screen. Normally, it's right side up. But in this case, it's like, okay, what if, go backwards. Okay. And forward. So there's basically this process here where what if you got tired of typing? You didn't want to use your hands anymore. You want to just be able to look at the screen, and then from the location of the person's eyes, it'll figure out like what word is being like the intention for the one to actually be performed. And everyone kind of looks a little bit differently. By that, I mean everyone's eyes kind of go at different speeds. They all kind of slightly look at different locations. So there basically this project, there was two different interfaces. There was one for using eyes, because we could run a lot of demos and some processing that way and to go over the actual algorithm. And then there's a second version of this for some anonymized user, where there was some very nice, actually really nice person that agreed to have an electro grid implanted inside of their skull. And it goes on top of the motor cortex that's on the right side of the brain. And here it's a grid. So it's, I think, 32 by 16 in order to lay on top of the brain. So there'll be two different forms of experiments. One will be using the eye gaze, and the second one will, like, after that algorithm has been trained and tuned, try it on this example where we have much less data. It's more or less noisy, but that sensor system, and the idea is the machine learning system is trying to infer, like, depending on the electrical signals from the brain, what is their intent right now for the word they're trying to actually like specify in order for a typing interface. Also, short story, yeah, the really nice person in question is like, somewhat movement impaired. So this is like, how do you make a systems for someone who is kind of like paralyzed from the neck down so they can actually type? And this is one way to go about it. Involves a lot of details. Okay, so we're at least clear on the two interfaces so far. Great. And then this is the process of being able to collect some data. So here we can use a combination of offline learning to basically train that individual data. Sorry, there's also an audio going on for this particular video that keeps playing. Okay, cool. I'll pause that. Maybe I'll just do this for now. Okay, so basically here, collect some data of some person looking at individual like words at any point. And in order to be able to save a lot of the data use, we're basically going to train something. It kind of looks like a VAE that then goes from like eye movements to like locations in the screen, such that at least the search later that for the intention space, which is going to be like over where the intention should be amongst these actual like 8 options that the person could look at with their eyes, then you basically only need to figure out like which one of these 8 binary choices is the person actually trying to attend to right now with their eyes or with their brain. Does that make sense? It's just sort of, it's lower dimensional, so it's going to be more data efficient for us to use that representation that we train from this data. The screen size was definitely fixed in this case. That was actually a really important thing to figure out and learn, at least for this particular project. Um, the short story for that one is there's kind of like an information bottleneck, but a physical one here, where at least you could only compute the differences in the eyes when there were only like 8 items on the screen. And when there were more than that, there was like not enough to clearly see between the differences in the way the person's eyes looked to understand what it was looking at. And this is actually very true for a lot of interface problems. Once you add too many choices on the screen, it becomes very difficult to differentiate between them. And then you could have less than this, but then it took longer for the person to be able to type. So we're trying to cut a balance between like trying to basically get them up to the fastest number of words per minute in order for them to be able to use this. But uh, definitely a fixed size screen. We also had to use a very specific computer. There's only like 3 computers in the world that can properly operate the hardware that connects to the brain computer interface. So we had to use that computer as part of the process. Yeah. Okay. Yeah. So you're asking kind of about the timing here. No, it goes a bit before that. I mean, it's not, these aren't just given out like these interfaces. There's like some of my colleagues at San Francisco University who are some of the crazy people that like both have a PhD and are also a medical doctor. So they're probably in school for like 40 years. But in that case, they like have to apply for grant funding much before this and then have the design for that particular piece of hardware before like the research even starts. And then there's kind of like an interesting call that's put out for patients such that like, do they meet the particular conditions? They still have to do it completely voluntarily in order to be able to agree to having this installed. Installed is a very interesting word. Maybe I spend too much time working with robots. Yeah. So that's kind of the process. It's sort of like hardware is created first, then a grant has to be put out because it's not just you can't just put this into someone's head. There's a lot of maintenance required. Basically, this person is now after that happens, like the person has to get regular medical like treatment and examination almost every other day. The device it works okay, but like electronics and biology don't always play well. So it needs to be like carefully monitored every day for any signs of like infection, things like that. Also, signs of infection interfere with the signaling process. So that's another thing that'll change the details from day to day. Yeah. Okay. And also, well, okay. So I'll get into some of the details for the project at 1.2. Because also the eye signaling was also a more standard way of collecting data. It was less non-stationary. Long story short, the goop that is inside our skull changes almost like every minute. So when we would record data from one day and we'd play it out like the next day and train a model on that, it would be different because just the brain signals and the connectivity of the brain changes all the time. So the actual signal processing that'll come out of this will also need to change. So We would collect data every week for a couple of months to kind of get an overall model that's a little bit robust to day-to-day brain signal rewiring changes. Yeah, this project took about 2.5 years, give or take, which I think is pretty good for any medical project. They normally take 5 years. Same person, yes. Mhm. Okay. And then this is them collecting some data. We also used with them like the slightly same screen size, but like less words on the screen to make it even easier to be able to kind of figure out some of the intentions. So in this case, we kind of like learned a bit of a model also that can go from like the brain interface to the visual tracking for the eyes to make sure things are working well. But then we can just go from like signals from the brain, selecting words so the person can actually type on this computer screen overall. Um, and then here we'd have sort of this interacting pipeline. And then here's where we kind of get down to the training details. Okay. So here there's basically, yeah, like a couple of different words. We collect some binary feedback, yeah, is what we also did from the user. So if when looking at the actual item, the person will push whether or not the system actually collected, like triggered the proper item inside the screen. So there was a version of this where we could also like train that encoding layer that would make things faster, and a version of this instead where you can go straight from visual inputs that go into this process in order to be able to create a system that'll actually select the right word in this kind of ring. Okay. And here, this is just like binary feedback, like yes or no, really just like one key if it did a good job, otherwise nothing, as a way to kind of do a bit of feedback into the overall system. Okay. In the end, so if we just use a default interface, so this is kind of like, I could think of it as like training a linear model on top of the actual data set. This was the performance it would get without like any online training of collecting data from the user feedback. And then this is using a method that we basically developed that processes over this actual image and then gets some feedback from the actual user. So this like online, a bit of feedback of collecting some of the input from the actual user does help make a better interface. Okay, yeah, and this is, uh, there's not too many people that have this particular setup, but it could be used in order to give them, at least in this case for typing. The goal for the next stage of this project was actually to be able to provide even more agency to these people, like this, such that you can maybe like control an extra robot arm or something like that. So you can use it to like clean the house, use it to feed themselves, things like that. That'll still be a work in progress, probably for a little while, no matter what people at Neuralink are trying these days. Uh, it seems like it's still going to be a process in order to be able to do this for a number of different reasons. As we've hopefully learned a little bit in the class so far, hardware is hard. Hardware and wetware is even harder. This would be one way to put this. Okay. Any other questions? All right, so then let's get back to the other slides for a second. Okay, so now is a bit of another choose your own adventure. So we can go through another brain-computer interface question, or we can start talking about versions of this that expand for larger models and things related to RLHF. So who wants to learn more about brains? And who wants to learn more about RLHF? Okay, sounds fine. I noticed there was also some squeamish people related to brain-computer interfaces, which is fine. I'm also not a fantastic fan of even needles or anything like that. So we can talk about RLHF, which is more or less worse. All right, so now I've got a trick question for everybody. So what is RLHF? No, I already apologized where it's kind of a trick question. What do you think it is? What do we think RLHF is normally used for? which sensor is better? Okay, two ways of doing something. Sorry, I'm having a little trouble hearing you for the air conditioner. Okay, it's pretty good. Anyone want to add to that or completely disagree with it? Go ahead. Okay, good. And then you happy with that answer, more or less? Okay. All right, good. So that's good, actually. These are actually mostly correct, but they're not RLHF. So what you basically just described is actually what should be noted as reinforcement learning from human preferences. And it's been grouped together kind of immediately without much of thought. I was like, no offense here, like the community has done this. So here RLHF is supposed to be from human feedback, but you kind of both said like depending on human preferences, which is a bit different. Like you did comparisons in order to be able to outline things, and you kind of mentioned that as well. And I'm just here to also be picky about all the people in like the language modeling community who have been using this for preferences. So RLHF is actually RL from human feedback, which started like 2 decades before language models, or at least LLMs were ever really created. But this is not so preference heavy here. This is literally like give the actual reward for that point, or like this is the action that should be selected at this state. That's human feedback. No, not preferences yet. So like the definitions you got are good so far. And this is different from supervised fine tuning. If people want to know more about that, there's actually a collab I created for my data science class from last term where you can go dig into supervised fine tuning for a couple of examples. If you, for some reason, want to fine tune an LLM to produce exactly the text files that are generated from Zoom from classes like mine. So if you want a data science LLM version of Glenn that'll give you answers to data science problems, you can go fine tune that. Um, but here we'll focus on this like human feedback version. So like the typical RL problem that we've discussed in the class is this. Like there's an environment, there's an agent. The environment gives all the rewards. That's where they come from, and the agent is just trying to figure out which actions to take in order to be able to maximize those rewards. The version of this that's more RLHF is based here. I'm borrowing this diagram from the Tamer paper, where now there's an environment, there's some agent learning in here, but the human is basically coming in and saying, okay, at this point in the environment, this is the action the human would take, and that gets a reward of 1. All the other actions basically get a reward of 0, something like that. And then the agent kind of like provides feedback for all the agents, for all the actions that it would take in that environment where the agent is right now, in order to help reward the agent for going more towards what the human wants. The human might have some idea for like what the modeling of its own reward function for solving the task. The human should have some idea about how to solve the task, but they're really just going in and providing these rewards. A reward function just does supervised learning, so kind of basic stuff, not the preference learning, in order to be able to learn a reward function from that. And then the agent will like use that learned reward function to like as a way to generate rewards for itself and train its policy. In those cases, we're not learning a reward function, which I know for the moment that might sound like good, because like, what do you need this extra reward function for? But in some cases, if it's really difficult to be able to collect like expert behavior, it might be better to instead just provide rewards. Like this is what I would do in this location. in the actual state space in order to have it be able to learn. One of the things we'll get to a bit later, though, is like also being able to do this with preferences is a bit of a easier way to specify the problem because it's actually very difficult to ask a person to be perfect. As much as I do it every day, the challenge is it doesn't really happen, but it is easier to ask a person to compare two things and say one is a little bit better than the other or way better than the other. And that's where some, at least like learning a reward model can give an advantage in that space. Okay. So it can slightly be used for the same thing, but the human here also doesn't have to provide a reward for every single action and state. They just provide like a little bit of data. So like even in the like BCI interface example I was just giving, the human only had to like provide labels at the very end of the episode, and then that can still be used to learn a reward function that can be used at any state over the episode. So it's kind of a way of trying to extract a little bit of a dense reward function, even from sparse data. Okay. Mm-hmm. So you're sort of asking like if the reward function already knows the best action, it can be used to help select. Yeah, it's one of the advantages of having like some model of the reward. Like there's a lot of power that we have, or we can use a lot of different algorithms if we even have a learned model of the reward. You could use it to compute a policy from it if we have a model for the reward. Otherwise, if we're just getting trajectories, I guess we can train a policy from that, but we don't necessarily know if that trajectory represents the best behavior either. So if you can learn a reward model, it is often a bit more helpful and a more reusable. Okay. Okay, so then let's kind of branch off for this and make some connections to this in language model learning. So this is also reinforcement learning from human feedback, or what should say from human preferences. Is something that's been done, I guess, obviously grown quite much popularity. Honestly, the thing that was most popular in terms of like what reinforcement learning has been used for in the last couple of years is to fine tune tons and tons of language models. And the idea is kind of like two-step. Like you can train a foundational model, even some of the robotics foundational models that we've talked about in the class, because there's some large amounts of data, not a whole lot for robotics, but a lot for text. And from that process, a good representation can be learned. At least like a better than random representation can be learned. And if it's better than random, that means, okay, it should at least help save a little bit of time or data when fine tuning to a new problem. But still, like more useful models are desired. And this is where kind of this useful concept comes in. So models that understand goals and how to achieve them can probably end up being a little more useful. We've kind of talked about this throughout the class. Because the challenge with just like training an LLM is it's really just trained to predict the next token. It's just this kind of babbling machine. The next step is like, okay, how can we now like adjust this model such that it becomes a more task-based thing? If it's given a sentence or something like that and a proper response that it should actually perform, how does it do that? Because at the moment, if it's just the LLM stage of kind of like producing like kind of text or tokens, not randomly, but just in a sequence, it doesn't really do this like conditioning and like task-focused answering very well. So a lot of this feedback process, it's at least used for language models, is to help provide this behavior. You can call it correcting it or something like that. But I guess I also don't want to take much too away from the LLM model, because basically if the LLM wasn't already trained, it's almost impossible to start from scratch doing reinforcement learning in order to be able to get to something that produces like good structured task focused behavior, with maybe, like DeepSeek R1 is like one exception that uses a lot of RL, but also had a lot of really nice environments for doing like coding and mathematics proofs that allowed it to train itself in an easier way. So this is like, in order to be able to help train them for goals, they need to be able to like better act on these intentions inside of the environment. So there's some examples. The one we were just talking about for robotics for a little while ago is already from 2008, and that was the like learning from feedback. There's some newer versions of this as well, and it's also been used in video games, and also a Canadian colleague of mine, which I'll always add, everything good always comes from Canada, of course, was doing some earlier work in this a while ago too, for figuring out how to adjust sequence generation models in general using RL, which is basically what we're going to talk about today, but in a couple of other forms. Okay, does that make sense so far? It's kind of like, how do we transform any generative process now into something we can use in terms of like giving it a task and it'll give us back an output that's actually useful. But the generative process, the generative pre-training process, provides some really good structure to start from. And if you want to know a lot more about this, you can go and read Nathan Lambert's book on just like RL fine-tuning. It's okay. I've been reading it over the last couple of days. It's definitely got some good details. Okay, so RLHF is basically used to turn the response and not the next token. So like the language model, the LLM is just trained, make the next token the most likely thing that appears given the context so far. And the loss function is just at this token level for being able to do like current context, predict the next token. So actually the loss changes when it goes towards RLHF, and not just like the loss changes, but also like the size of the input and output changes. Because now the model is going to actually be given rewards, like increase the likelihood of this whole trajectory. Because it's not just being rated on like half of the response. The response has to be good and make sense and go along with the actual input. It's the stuff we're used to thinking of when we do RL. So that at this point, it's sort of like, now it's not just next token, it's like get the whole answer phrasing correct. And this kind of change in the actual training process helps make the outputs much better than what they were just from pre-training. And then from that, just kind of like rank responses. So language model can be like queried to produce a bunch of different responses. People can like thumbs up or thumbs down, basically the responses that are outputted. And then from that, it gets a bunch of preference data, which ones are better. And then from that, train this reward model in order to be able to, again, be used. So it's kind of like train a reward model, because then you can just use that with a whole bunch of compute to query that reward model a bunch and then use that to train the policy. So it's not like for every query the person does the labeling. There's an artifact that's the reward model that is used to actually rate all the trajectories. Okay. Makes sense so far? Is everyone already like super familiar with RLHF and has already programmed stuff in RLHF? Okay. Not surprising. Also, I was actually a bit surprised when I was going over all the papers I could find. There was no robotics RLHF paper, if you know what I mean. Like there's no figuring out how to take an LLM and then fine tune it on like robotics questions. That of course I would have only those questions, not like whether or not this thing is like some biology question. But I think it could be a fun piece of research to just figure out what is RLHF for robotics and everything that's related to robotics problems. We'll cover one paper at the end that is as close as I could find to that problem. Okay, but so we're doing more robotics in this class. So I want to like introduce as much robotics related stuff. So preferences, you can think of them as like the sentences of like, I don't know, biology answers, but let's just do RL again. So we can look at them as like difference in behaviors from like the robot. So here is an example where we're going to start, and let's like ignore the LLM part just for a minute, but we want to be able to train a policy based on preferences. So first, need to be able to collect this data, where basically there's just this preference of like I is greater than J at whatever the actual task is. And this greater than symbol just means better. And one of the earlier works on this, I was just using for this for RL was to figure out how to do this process to train a policy. So rather than collecting like labels at every, or at least a number of actions for like, this is the action that should be performed here. Now there could be a policy that's basically generating a bunch of trajectories. And then a person can come and label, okay, no, this trajectory looked more like a backflip than this other trajectory on the right. And then from that process, then generate a new set of possible trajectories from this agent, and now have a person again label just a couple of comparisons. And then eventually there'll be kind of like this like ladder of preferences that lead towards, okay, no, this one, once all these comparisons are made, this one now looks most like something that's a backflip, just from all these comparisons. Okay, does that make sense? Let's see, how are we doing? Not too much time. Okay, I'll do this one real quick just to give an example, because I know this is only a picture, but this has got a fantastic website where you can even go and like load this up on your computer and be able to do these comparisons, and it'll learn inside of your browser. But this is basically it, where you can roll out a couple of trajectories, or you can think of it as like the robot that's trying to help you out in your house. And it's going to try to clean the kitchen like 100 times over the year. And then you can start to like record the videos of it cleaning the kitchen at different points, and then rate which ones were better jobs cleaning the kitchen. And then it'll learn a reward function from those preferences to then get a policy that'll produce like the best behavior for cleaning the kitchen based on what you thought, like how you basically selected between these trajectories. Okay, does that make sense? I just find this is a little bit better than just like asking sentence-based questions, since we're learning about motion control here. Okay, but feel free to dig into that a bit more later. But this is basically going to take this process, at least for like language models in general. Now, instead of videos, it's going to have, you know, sentences and things like that it's trying to choose preferences over. Yeah, what's up? Hmm. That could be possible. So yeah, like your question is, I don't know, maybe in this case, what if the tiles on the ground have changed color a little bit, or like the lighting in your house changes, or the season changes, so now the sunlight comes into your apartment at a different angle. Um, that would be more of a representation learning problem. At least that's where I would suggest to start, because those aren't as task related, at least for like the tile color example I'm giving. But if there are other objects and now the robot interacts with different objects than it did during the previous sequence, okay, that gets a bit more complicated. Or some of that can be handled with a representation learning like method to say like actually some of these states are the same. You might still need to collect other trajectories. The hope is, and what seems to be part of like the beauty of like the RLHF paradigm is, okay, if the generalization would hopefully be learned inside the reward function between preferences. So like even if objects change, if the notion is just clean kitchen, I would hope it would still generalize across just identifying things that are like should not be on the counters, even if they're only used at like different points and different trajectories or on different days or not at all in some other ones. So a lot of this, to be honest, is really like situated, like the foundation is the reward function is going to provide a lot of generalization. And that's where the preferences hopefully come from as well. So like with few preferences, a reward model is learned, and then that is used to like fine tune like billions of possible queries to a language model, even though only data on like a million examples is collected. Probably a bit more than that, but so the hopefully in the reward function handles with generalization. So here just to go over like the objective functions to how to train this. It will probably be a bit short on time. So you can go back just a little bit. This is just a version of a Bradley-Terry model for like how do you get an objective function to actually train a neural network when all you have is comparisons that says, you know, I is better than J. So from here, if you've got this process where basically we want to make the probability, of I basically better than the other two, the sum of the other two, if that's what we actually have in our data set. So we can construct like this loss function that's just like the reward for these two. And remember, we're training the reward function here is what I'm talking about, not the LLM yet. Looks like there was a bit of a miss here for some of the notation, which I'll check over later. But I believe this is supposed to be y of L, where like L is like loss as in it wasn't the better answer, and y of like winning here seems to be the better one. So you can use this loss to actually be able to train the neural network here. So it's going to be, you want to be able to increase the likelihood of the things when it answered y for the proper answer, and basically decrease the likelihood of these other examples for x for the things that were not, judged to be the better answer given the human feedback. There's a couple of other details. There's also one other way to formulate this loss function, but this is the loss that you end up training. What this ends up looking like, just in like PyTorch code, is just NN functional, a little bit of a sigmoid because you need some probability distribution now for these two comparisons. These are all of the outputs that were chosen to be correct, and these are all the outputs that are chosen to be like at least not as good as the chosen versions. Compute the mean for this. Perform this a couple trillion times, depending on how large your language model is, and then use this just to compute a gradient over trajectories. This kind of part is like train the reward function, do policy gradient. And most we'll get to this a bit later, but like a lot of them are using reinforce, which we hardly even talked about in the class because it's like the simplest policy gradient method from 30 years ago, but it seems to work really well for RLHF. A hypothesis there is RLHF doesn't have a lot of variance. Like the distribution over possible outputs is not a lot because it's been fine-tuned that way. So doing things like PPO and having clipping terms and worrying about variance in the policy gradient is not the problem. Just being able to get a gradient is the problem here. So you can use simpler RL algorithms. Okay, good so far. All right, and then the challenge is that this process still runs into a lot of the problems we've basically already talked about in the class. So now there's a big giant model, but that reward function is very prone to like over optimization. It basically becomes overfit on the data in some way. And then because of that, when you train your model on this learned reward function, it doesn't actually represent the preferences. It's going to find a bunch of corner cases and optimize those a whole bunch and not actually result in very good performance. So this is some of the methods that need to be used. It's like, well, now this optimization process needs to be regularized. One way to do this, it's actually really similar to that paper we talked about in the offline RL lecture, where I was trying to figure out how to go from offline learning to online learning. But in those cases, it always needed to keep around all the offline data, because if it didn't, there were like challenges with optimization because all of a sudden the data distribution shifts a lot and the statistics from the optimizer change. So a lot of RLHF algorithms will do the same thing. Like they'll basically keep around a pile of the data that was used for RLHF, include that in like half of the batch when it's optimizing, and that'll keep it from changing too much as a regularizer. It's also used a lot for, seems the instruct GPT algorithm. One other way that's also a really common way of doing this is just to regularize the model to the pre-trained model. So sure, optimize using RLHF in order to be able to improve the rewards that's been learned from the preference model, but then constrain the difference here. So like this model can now not be too much different than the original model that was trained with the just LLM loss. And this can keep it from getting too far off track. This also looks like really similar to PPO when we talked about it. It's like try to optimize the reward, but don't get too far away from at least the previous set of parameters. But now these parameters are fixed. Like the LLM doesn't change. This is always just like a big weight that's like holding the LLM from changing too much and getting too far away from its original data. And this seems to be part of the art in being able to get RLHF to work really well, or at least like reinforcement learning from human preferences, is this balance between these two. There's going to be some amount of change relative to the weight on this KL term for how much the outputs can change. And if you get that right, then it'll change just to correct itself to be good at the optimizing the reward function for the preference model and not get too far away from what it did from before. But sometimes, making the most out of this budget is basically like a bit of the art now, like trying to figure out how to do this optimization well and still being able to get good performance while not totally degrading performance. Because definitely one of the challenges that happens in RLHF is when this process starts, the diversity of outputs out of the model shrinks a lot. So then it's actually like, if this is just one reward function, it might learn some like average response that just says like robotics is the best thing in the world, and that'll be like good for a large number of answers rather than having diverse outputs depending on the actual input, like which is the state or the prompt, something like that. Okay. Does that make sense? Any questions? This is like the 20-minute, pretty condensed version of RLHF, but it's actually a bit easier to talk about in the class because we've covered like every component really that's used for RLHF in the class already. There's just a few details on, I've got a big model and it usually takes a cluster of like minimum like 8 A100s in order to be able to do the smallest version of RLHF on just like Llama 7 billion. Okay, so there's maybe only 0 minutes left, but it means I'll just go through this kind of quickly. So I was kind of started with this question, like, so then how do we do this for robotics? Short answer is it hasn't been done for robotics yet at all. So you're maybe welcome to explore that or think about it. The closest paper that I found was actually like using RLHF fine tuning on a VLM, but it does more what we talk about in the class, as in like there's a reward function in the environment. It's going to use that to fine tune the VLM policy in order to be able to do better on that reward. So there's no preference model here for like what is better behaviors for a robot. This is very specifically like fine tuning for some of these games. It just tends to turn into, in these problems, as much as it happens for robotics, training large models is a lot about like infrastructure and tooling. So it's still very much the RL loop. There's maybe a bit of filtering in the environment so that it doesn't select output actions that make no sense at all from the VLM before they enter the environment. Use some reward model to label that and use the replay buffer to keep that data and just use PPO. So I guess go a bit quick through this because it really is just like do PPO, replace the policy with a VLM, try to get that to train. A couple of more details in the paper. Yes. So that's what I would call like what I sort of mentioned a little bit ago. So that's reinforcement learning from preferences, which what seems to have a little bit more power than this, which is still like a version of reinforcement learning from, it's not even human feedback, like it's just fine tuning a VLM. It's using the reward function in the environment. So this isn't really exactly doing what we just talked about for the last 20 minutes. So there's no like looking at trajectories for different agents or from this VLM model and then rating them to be better or worse. This is just like using the reward function in the environment. Maybe I missed something, but I couldn't find a paper that did like RLHF stuff directly for robotics or for preferences between trajectories. This paper is probably like the closest thing, and this has probably maybe been applied to robotics. Maybe I should have looked up robotics reinforcement learning from human preferences instead of human feedback. I might have found what I wanted, but I haven't seen this applied too much. I think it's also just really difficult, maybe related to even your question of like, you need to collect trajectories across robots and it's going to look appearance different as well. And there might be different objects. So it becomes really hard to rate trajectories across robots overall. Okay. Mm, right. Yeah, basic things done. But I think there's two challenges there. One is it's really hard to compare two robotics trajectories and know which one's better unless you're an expert in them. And then it's still two trajectories of visual data, which is not really what's ever been used for RLHF or from preferences. So that might be one challenge. An easier to achieve thing might be like just do this over text-based plans for a robot. Like ask just an LLM, okay, if this was the scene described in text, and does it actually output like two versions of plans and then rate those to be better? And that could be at least used to like train the backbone that's put in some of our larger VLA models. So just like maybe Llama can be fine-tuned on robotics problems, and we can use everyone here in the class to rate different trajectories that Llama produces for some planning problem. And then it can learn some reward function from that and then fine-tune Llama on that reward. But we probably need like people with enough robotics skill to look at the plan, which is still not going to be easy, and understand if the output is good. So I think RLHF also works when there's a lot of data about what the solution is already. And many other questions are easier to ask the average person and collect a lot of data. So I didn't really talk about data very much, but like these companies are spending billions of dollars paying other companies to collect data and preferences for them. Even there's like some colleagues I've got, it's actually maybe a good sign, like the people at Cohere, they're like hiring many, many PhD students to help provide preference data because they can answer the hard questions the language models can't handle yet. Okay, I'll stop there for now, but I can answer some more questions for people that want to hang out. But otherwise, have a fantastic weekend. I'll see everybody on Wednesday. Sure. Let me just